Good morning, everybody. Where'd everybody go? They're scared now? Hold off talking about the exam in public for another couple hours. I'm still trying to meet up with some people that need to take it and have had bad things going on in their lives. So try and clear that up. But I'd say by 11 today, right? You could feel free to talk about it. Yeah.
So it is okay to feel now that I need to throw up?
Yeah, throwing up is normal. Yeah. You said throw up, right? Not grow up? Both of them. Okay, yeah. But yeah, no, I know you're going to be nervous and distraught and you're going to freak each other out when you share information, right? Who would you do on this one, blah, blah. I'm not going to talk about it till Thursday, right? I'll be grading them today and tomorrow and all that kind of stuff, but I will withhold any information till Thursday when we can talk about the exam autopsy and all that kind of stuff, right? So you can ask me, but I'll just say, well, I'm going to talk about it on Thursday. But what we got to do is we got to look forward now, right? We've got to push on, right? And what we're going to do for this next unit, really for the next 3 weeks, is talk about forces and energy. You've gotten kind of one of the 4 toolboxes that we're trying to give you this semester is kinematics, right? So how things move, predicting where they're going to be. And so what we're going to do now is we're going to talk about why things move. Brought to you by Freaky Dude. Like, I don't know about you, but doesn't that just creep you out? It's in the eyes somewhere. I'm not sure the painting caught the likeness all that well. Maybe it did. I don't know. Who's this? This is Isaac Newton, okay? Genius, no doubt, right? Really the father of physics as we know it today. Before Isaac Newton, physics didn't exist. After Isaac Newton, it did. It's hard to sort of overstate the impact that he had on making modern science the way it is. Before him, it was all sort of just natural philosophy. It was, everybody was kind of doing everything, geology, chemistry, physics, mathematics. It was all wrapped up into this one idea. And after Newton, we really start getting this separation of subjects. But make no mistake, Newton was a jerk. He was not a good person, okay? And this, I mean, we sometimes glorify, right, these founding fathers, so to speak, and all that kind of stuff, and some of them are great, but some of them are just, pun intended, they're bad apples, okay? And Newton was kind of this bad apple. Genius, no doubt. The work he did in physics, amazing. He didn't treat people very well. He spent more than half of his life trying to suppress the work of others that contradicted his own, using his position and influence to do so. So while we venerate the physics, right, the science, what he laid down in terms of our understanding of how the natural universe works, I think we need to be careful about venerating the man. So we'll move on and so this is what we're going to do. As your tour guide through how the universe works, I'm going to approach Newton's laws in a weird order. We're going to do the first law, then we're going to do the third law, and then we're going to do the second law, because it's the second law that we're going to spend a majority of our mathematical time with. And so today is really kind of a conceptual tour through Newton's laws, forces, all that sort of stuff. We'll start laying down some of the graphical and mathematical tools we'll be using, but really we're going to kind of use a lot of that on Wednesday. Somebody want to tell me what Newton's first law is? I know you've heard it in some way, shape, or form, even if you didn't read the book. Object in motion stays in motion. And what does an object at rest do? Stays at rest. That's because rest is a state of motion. This is where you look at me and go, Mr. Balogh, physicists are weird, right? We all know that something that's just sitting there isn't moving. And I'm like, well, it is. You just forgot to consider that it's moving through time, right? So physicists, a state of motion could be zero motion, right? It's still a state of motion. So Newton's first law is this statement. And it's a statement about what things really want to do when, like, why do things stay in motion? Why do things stay at rest? There's like a but in Newton's first law. Unless they are acted upon, unless some outside... Okay, what's a force? Not the force. That's different. What's a force? Okay, all right, let's do an experiment. Let's do it. All good science based on experiments and data, right? Okay, so I want you to turn to your neighbor. If you don't know their name, introduce yourself and ask for permission. Okay, and if you don't get the permission, you do not do this, right? Ask for permission for you to poke them in the shoulder and then let them do that back to you. Go. All right, stop touching each other. Stop touching each other. It's getting weird. All right, so what happened? So some of you were kind of, it feels good. What happened? Nothing? I was moved. What? Life happened. The universe distilled. What is a force? It's a push or a pull. That's it. That's what a force is. Try not to make it any harder than that. Anything that is pushing or pulling. And we're going to give it names. We're going to give it names like friction and the normal force and tension and all these different things, right? But at its core, a force is a push or a pull. Forces cause things to happen. They cause motion to happen. They cause things to turn. They cause them to speed up, slow down, all those different things. But a force is a push or a pull. And so Newton's first law is this statement that things, in order for something to change its motion, we need to push or pull on it. We need to apply a force to something in order to get it to change its motion. Now, what's the symbol we use for position? Like mathematically? X, Y, Z, right? We use these symbols to indicate kind of where we are, right? What's the symbol that we use to indicate motion, that something is moving? It's a vector. It also starts with V. Velocity, right? Velocity is motion. So what is the symbol that we use to talk about change in motion? Acceleration. So, when I say that you need a force to change the motion of an object, what am I talking about? Acceleration. Forces cause accelerations. If you have a net force that's not zero, and when I say net force, what is that code language for? All of the forces acting on something, right? A net force that's not zero, you're going to be changing the motion of an object. Okay, Newton's first law is also called the law of inertia. Inertia is a kind of a funny, weird thing. You've got a feel for it in your gut, but like its definition is a little bit, it's kind of, it's not broken. It's a good definition, but it also doesn't, it's kind of like a backwards definition. You really want it to be more succinct than this, but it isn't. What am I trying to say? Inertia, the more inertia something has, the harder it is to get it to change its motion. What has more inertia? A bicycle or a car? Car. How do you know? Ooh, okay, I haven't talked about mass yet. The M word's coming up. Weight is negotiable because we can go to the moon and the weight can change. What? Friction? Oh, yeah, like when you try to go push on it, right? Which one's harder to get moving? The car. And so we say it has more inertia. Like the inertia is this quantity, like the more something has, the harder it is to change its motion, right? So we're orbiting around a concept, the M word, which is coming up, okay? But inertia itself is a measure of how much an object wants to maintain its state of motion. Something with a lot of inertia that's standing still doesn't want to start moving, right? Okay? Or is harder to get it to start moving. I like to think of trains, right? If a train's sitting still on the tracks, you can push on it all day long, right? Okay? But once the train is moving, how hard is it to get it to stop? Pretty hard, right? And so trains have a lot of inertia. So I want to play some videos for you, just some demonstrations that we either don't have the time to set up or we don't have the budget to screw up.
We'll try to remove the tablecloth from under these dishes without making a mess. How? By yanking the cloth out very fast.
That wasn't a yank, that was a
Pull
pull.
slowly and the table setting moves.
We got that.
This will have to be done much more quickly.
Candle is very important
A
in this
metal
demonstration.
tube wrapped inside the loose edge of the cloth provides a firm grip for a fast pull. When the cloth is yanked out fast,
Ooh!
the dishes barely move.
Okay, all right. If you are going to try this at home, I would say don't attempt this at home. But if you're going to try this at home, please make note of the following. If you set up your mother's dishes on a tablecloth and grab the tablecloth and yank, you will fail. You will fail this class, you will fail your mother, you will fail everything, okay? Because there's a trick. Did you notice the trick, the thing that made this work? There was a bar on the edge of the tablecloth. It's very, very important, okay? Because we need the entire surface of the tablecloth to be moving in the same direction. If you grab the tablecloth at just one spot and pull, now you've got like a bunch of different vector directions for all of those forces, and they're all going to be pulling at different amounts, at different rates, and it's going to be bad. Okay? So make sure that you put a broomstick or a board or something along the entire line and make sure you pull consistently on that tablecloth. Then it will work. Do it quick.
Can you do it?
Yes.
Like actually?
Uh-huh.
Can you do it in the lab?
If you guys remind me, the problem is that the chemists don't like it when I break their glassware. Right? So if I screw up, I've done it many times, but like if I screw up, it's bad, right? And I asked them to buy me tablecloths, but they're like, who do you think you are? Like, you tablecloths for class? Like, no, I was like, demonstration purposes. They wouldn't buy me diamonds or gold or anything else. It's kind of weird. But more importantly, why didn't the dishes move? Okay, well, they did move. Remember, did you notice how I pulled it slowly and they moved? So there had to be some friction between the dishes and table. We haven't talked about friction yet. That's next chapter. Okay, do the dishes have inertia? Yes, right? This property that states that you got to act against this inertia to change its motion. When the guy pulled the tablecloth slowly, the friction had an opportunity to work with the object, right? But when the fast pull happened, inertia won, didn't it? The plates and everything stayed in the same location. They did drop a little bit, right? Okay. Make sure the tablecloth doesn't have a nice furled edge or something like that. It catches all the dishes and they go crashing down. I have to show you this one just because. They won't let me build this one.
We will blast a pencil through a piece of plywood using a carbon dioxide fire extinguisher. A pencil is inserted into this tube, and the carbon dioxide fire extinguisher is connected to the end of the tube.
That's right.
When the fire extinguisher is activated, it will drive the pencil through the tube
Wait for it.
into a piece of plywood positioned at the exit of the tube.
Wait for it.
Here is the action repeated in slow motion.
Okay, let's do an experiment. I'm gonna give everybody a 1/4-inch thick piece of plywood. I'm gonna give you a pencil, right? And your grade depends on your ability to get that pencil through this piece of wood, right? You get the pencil through the piece of wood, I'll give you an A. If you don't, you get F. What happens? Blood, right? You guys would be like, ah! Right, okay? And you would have splinters, and it would be bad, okay? It would just be bad, because no matter how hard you push that pencil into that wood, is it going to go through? No. Why did the pencil go through the wood there?
Because it wasn't the speed of the bullet.
It was going very fast. So again, we're kind of back to this idea that there's some sort of time thing here, right? The dishes, pull it out fast and the dishes don't go anywhere, but go slowly and other forces have a chance, right? So again, this is about inertia, right? The pencil, in a sense, has a lot of inertia. It just wants to keep moving and it doesn't care if the plywood's there. Now, does the plywood eventually stop the pencil? Yeah, right? You saw that the pencil only made it like halfway through or so, right? Okay? So there, the force of friction between the plywood and the pencil, it eventually stops it, okay? But again, we can apply tons and tons of force to a pencil and to plywood and never get through if we do it slowly versus taking advantage of inertia and having it happen quickly. So if the first law, right, just tells us that forces exist, it tells us what forces are, and it's hinting at this concept and idea of mass. We'll call it inertia for now. So let's talk about Newton's third law. Okay, again, skipping the second, we'll come back around to it. I'll bring the lights up in a second because I got more videos. So, what does Newton's third law say? Yeah, okay, so there's two objects, right? If something exerts a force on the other, what do we know about the forces? Equal and opposite. Okay, all right, okay. Equal what? What does that mean, equal? It's the same magnitude of force, right? In our demonstration earlier where we poked each other in the shoulder, right? You poke them, right? You apply some amount of force. According to Newton's third law, what force did the person apply back to you? Equal? You're like, no, Mr. Balogh, mine still hurts. I poked them gentle and they came in. Ah! That's a different set of forces, isn't it? Because the forces we're talking about here would be the finger and the shoulder, right? If you push in with 2 pounds of force, what's the shoulder going to push back with? 2 pounds of force. That's what we're talking about, right? So Newton's third law reminds us of several things. Number one, forces always exist in pairs. You can't have a force all by itself. And in about 10 minutes, you think I'm going to break this rule, and I won't be breaking it, and I'll get to that in a second. Okay? But forces always exist in pairs. Okay, Mr. Balogh, if you're so smart, what about gravity? Gravity is a force, right? Okay? Who's pulling on who? Where does the force of gravity come from? The earth. Okay? The earth is pulling on us. We're trapped in the earth's gravitational field. The earth has a lot of mass. Earth pulls us down. And it seems like on some mornings harder than others, right? It's not the force of gravity changing, it's something else. So if the earth pulls on me, what does Newton's third law say? Me pulls on the earth. I didn't pass English. Wait a sec. Wait. If the earth pulls on me, I pull on the earth? Newton's third law says that when two objects interact via a force, right, that the forces are equal and opposite. So I know this morning that the earth was pulling down on me with 173 pounds of force. How did I know that? Stepped on the scale, right? Okay. Scale is trying to indicate to me not my weight, not the earth's pull on me. What's the only thing the scale can tell me? Careful. The force on what? What two objects are interacting when I step on the scale? Scale and the Mr. Balogh. Right? It's not the scale and the earth. That's something else, right? Now, because my bathroom wasn't accelerating, more on that later, okay? It just so happens that the amount of force I exert on the scale and the scale exerts on me is equal to the force between me and the earth. But that's because I'm not accelerating. We'll get to Newton's second law in a bit, okay? But when objects interact through a force, a push or a pull, right, Newton's third law isolates us to those two objects. So back to the earth pulling on me. If the earth is pulling on me with 173 pounds of force, what am I doing? I'm pulling back with 107. I am? Can I move the earth? Demonstration. You ready? Okay, here we go. I'm going to move the earth. Ready? Did you feel it? Did you feel the whole earth? No, it didn't. Right? Why didn't the earth move? Because it has 5 point whatever times 10 to the 24 kilograms of mass. And I don't. Right? I only have 70 kilograms of mass. Right? It is big. Right? And so my little teeny tiny man is not going to do anything. Right? Who has more inertia? Me or the earth? Be careful. The earth. Right? So it's going to win. Videos. Anytime a fire extinguisher is involved, it's a good day. Oh, it's a bad day. Bad day when a fire extinguisher.
The spray from a carbon dioxide fire extinguisher looks a lot like the exhaust of a rocket. And like a real rocket exhaust, the escaping CO2 can accelerate a large mass. We'll use this extinguisher mounted on a rolling wagon to accelerate a person to suborbital speed.
Safety goggles, that's good.
3, 2, 1, blast off.
Go! Ooh, fast! Where'd you go? Aha!
Engine cut off.
Why did she go? What pushed on what to cause that wagon to go? Okay, let's get rid of the earth right away, okay? What direction is the earth pulling on the wagon person thing? Down, right? And did this person change their object in the up or down direction? No, okay? So whatever the earth is doing, it's not helping with this, right? Let's just get rid of it as part of our, okay. So what direction was the force that got this thing to change its motion? like horizontally, right? Along the ground. Are we in agreement, right? Because it changed their motion, right? Okay, all right. So we have the wagon, and we'll just sort of like the person, the wagon, the fire extinguisher, it's like all one object, okay? So what is it that either the wagon pushed on or the same thing that pushed on the wagon to make it go? CO2, the carbon dioxide. Which way did the wagon push the carbon dioxide? Backwards, right? Okay? So the carbon dioxide pushed how, according to Newton's third law? With the same amount of force in the opposite direction. What are the two objects? The wagon and the CO2, right? What did they do? They interacted through a push or a pull, in this case a push. Wagon pushed the CO2 backwards. CO2 pushes the wagon forwards. Did we mention anything about the ground? No. Did we mention anything about the air? No. Would this work in space? Yes, because Wall-E. Wall-E. You guys seen Wall-E? It's like one of Pixar's best animated films. Like, bar none, the first 40 minutes of Wall-E is animation gold. There's like hardly any speaking, right? And the animators did a fantastic job.
But like in space, well, never mind. I figured it out. Okay, never mind.
In space, no one can hear you scream.
I was gonna say like why can't sound travel?
Oh, okay, that's different. That's physics 4C. But the short answer is there's no medium for the waves to travel in, because sound needs gases to go through, or solids. But what did Wall-E do? So, spoiler alert, Wall-E dies. No, okay, but he doesn't, right? It's classic Disney thing, right? It looks like they're dead, but they're not dead. Sleeping Beauty, all that kind of stuff. Okay, so Wall-E's in this pod, escape pod, and the escape pod blows up, right? And Ava is out there trying to rescue Wall-E, right? Okay, and the escape pod blows up, and the sad music, and the sad Ava, right? Okay, but Wall-E comes screaming out of the debris with what? A fire extinguisher, right? Wall-E's holding a fire extinguisher. I would show this to you, but then Disney would come after me and you'd never see me again, okay? I'd end up being Goofy at Disneyland or something. Wall-E, which way does Wall-E point the fire? If Wall-E wants to go that way, which way is he pointing the fire extinguisher? He's pointing it in the opposite direction, right? Because Wall-E knows that if he pushes some carbon dioxide backwards, that the carbon dioxide has to do what? Push him forwards. Right? That's the essence of Newton's third law. Newton's third law, it isolates the two objects that are experiencing the forces and tells us exactly what those forces are going to be. Equal in strength, opposite in magnitude. If there was no force, it would just stay in place, yeah. So, if Newton's third law says that the forces are equal and opposite, right? This means I cannot lose, right? I just can't lose. If I run directly at that door at full speed, Newton's third law says that the forces will be equal and opposite. Like the building cannot exert any more force on me than I exert on it, right? So I can run full tilt in that door and be okay? Oh yeah, Mr. Balogh. Let's see that, Mr. Balogh. Everybody wants to see their physics teacher hurt for some reason. I don't understand. But if I did that, I would get hurt, right? Why? The building can take hundreds of pounds of impact, right? I can't. I'm old. Fragile. So, Isn't there a lot of stuff to remember in Newton's third law? Seems like there's just sort of a lot of parts to this, okay? So I want to offer you something, okay? And it comes with some conditions, but when this is over, if you guys decide to accept, I'm going to give you the choice. I promise and guarantee, money back guarantee, that you will never forget how to apply Newton's third law. I can't tell you what this secret is until you all agree to do exactly what I say for the next 3 minutes. Your safety depends on it, okay? And I'm asking you to trust me. I'm not asking you to do anything indecent or immoral, okay? But I can't tell you what it is until I get full agreement from everybody. So what do you say? You want a foolproof way to never forget Newton's third law? Or not? Like, just struggle with it? You good? Yeah? Only one person said yes. Yes, yes, yes. And the rest of you that aren't saying anything are just going to be bullied into acceptance? Okay, close the doors. Social pressure. Yeah, we're really gonna use that social pressure. High school is back, everybody, right? Social pressure. Okay, because we definitely don't want this getting out. And never mind, this will be on YouTube. It's not going to get out, right? Okay. So, do I have everybody's solemn commitment that you will do exactly what I say for the next 3 minutes? Yes? Okay, yes, Mr. Thank you, Mr. Balogh. We'll do whatever you say, Mr. Balogh. Get a name, Mr. Balogh. Okay? I am going to teach you, and you are going to repeat to me the Newton's third law song. You promised? You promised anything saying, yes, we are going to sing a song together, and I'll explain why this works later. But let me explain the song, and we're going to sing the song, and then we'll talk about the aftermath, okay? So the Newton's third law song is a trick to help you remember several things. And we're going to, as a demonstration, let's do the binder and the table. You got to kind of have to start with objects in mind, right? The binder's sitting on the table, and so I want to know what Newton's third law says about that. So I am going to demonstrate the Newton's third law song to you. And those of you that are still conscious after listening to me sing will repeat the song. Are we ready? Okay. This is how the Newton's third law song would go. If the table exerts a force upon the binder, then the binder exerts a force upon the table. You guys didn't clap. You failed. No, it's too late. It's too late. You get nothing. Nothing. No. Notice that the song referenced two objects interacting with each other, right? So sing along with me. Get your best shower voices out, right? And sing the table first. You ready? If the table exerts a force upon the binder, then the binder exerts a force upon the table. That wasn't bad. I've heard a lot worse. Little like Charlie Brown mumbling is usually what I hear, right? Okay. All right. Why is this working? Why is this guaranteed for you to never forget? Because you made me sing in public, Mr. Balogh. And the emotional trauma alone will sear this up my brain for the rest of my life. You will leave this room a different person because I made you sing in public, right? Okay. So the emotional trauma stays. Right? Okay, and this is one of those, right? I kid you not, students have come to me years later. Mr. Balogh, I still remember the song. I'm like, that's it? That's all you remember? Okay? No, but like, right? And I've watched students like on their exams, right? Say, right? Okay? Trying to remember. Okay? So what does the Newton's third law song remind us of? How many objects? There's always two. There's only room in the song for two, right? And the trick of the song is sort of flip-flop their order, isn't it? So let's sing the Mr. Balogh in the earth. Okay? And by the earth, I don't mean the floor. I mean, ooh, okay? So sing earth first. Are you ready? If the earth exerts a force upon the Mr. Balogh, then the... That was a little bit worse. Okay? But no, I'm not judging. Right? But again, did the floor get in the way? We mention anything about the building? Interesting. Okay. Let's get really violent. The bullet and the gun. Okay? Right? So sing gun first. You ready? If the That was good. That was good. I'm getting you on YouTube. It's great. I can make you all AIs now. All right. So, what's the bullet pushing on a gun called? Recoil. Right? That kickback of the firearm. What is the force on the bullet compared to the gun? There's only one answer according to Newton's third law. The same. Same? Soccer ball and my foot, right? Okay? I run up and I kick that soccer ball. Which one experiences more force, the soccer ball or my foot? Good. They're the same amount of force. Mr. Balogh, soccer ball. You don't run up to soccer ball and go boing. How can the force be the same and yet the soccer ball go whee? I have more inertia. Right? And now we're kind of getting back to Newton's first law, aren't we? Do they come together? Oh, yeah. All right. There's another form of Newton's third law, like a visualization that helps to really kind of understand what's going on here. And by the way, Newton's first and third law have no math. They are entirely ideas and statements. This is why we're not doing any math right now. Okay? So to demonstrate this alternate form of Newton's third law, I need a volunteer. I need somebody that can lift up approximately 173 pounds. You good, Liam?
173?
Yeah.
Why not? I can try.
Okay, come on up here, Liam. He can try, he says.
Are you 173 pounds?
I am 173 pounds. Okay.
Okay, I'm here.
Do you have medical insurance?
Hopefully not.
Hopefully? Okay, all right. All right, so Liam, would you please pick yourself up? You lifted your leg. I'm impressed. No, you pushed on the ground. That's cheating.
I am cheating.
Yeah. Can you? Yeah. How does he pick himself up, right? He tried a little bit. Let's look. Liam, can you pick me up? Go ahead. Wrap your arms around me. There you go. All right. Woohoo! Okay, put me down. All right. Give him a hand, everybody. Any massage therapists in the room? So why is it that Liam and I were not able to pick ourselves up? There was only one object. What would the song say? And the Mr. Balogh, search for Mr. Balogh. It's only one object, right? Now, why was Liam able to pick me up? Two objects, right? Two objects are required for a, but some of you are saying, but Mr. Balogh, if you take your fist and you, it's two objects, your head and your fist, okay? And yes, I know we can get into the weeds very quickly about what constitutes an object and all that kind of stuff. And you'll sort that out as we go. It's a little bit overwhelming to try to get down that line of reasoning at first, okay? So, where did my keynote go? Okay, so Newton's third law can also be stated as you can't pick yourself up. It kind of summarizes the whole idea. There needs to be two objects in order for a force to exist, which means there's always a pair of forces lurking somewhere, even if we don't always think about the other one. Okay, I think it's time for a quiz. Time for a quiz to see how well you're doing on the concept of this stuff. So let's keep going. You work with this stuff and your brain will start to see the patterns and things will start working. And you're like, you're such a liar, Mr. Bailey. You said that about the first stuff and I still don't know what I'm doing there. All right, which is normal. Save the best for last or the worst for last? So, there's, I guess you could say Newton's second law in words, but it's really awkward. Newton's second law is best expressed in math. And I'm going to write it a different way than maybe you're used to seeing it. I'm actually going to write it several different ways. But this is the way that I like to write it the most. You'll see this a lot. Sometimes you won't see the squiggly E. The way that your book probably does it is something like maybe this, right? Or maybe they put, what's that squiggly E mean? That sigma? Sum up, add up all. Sometimes you'll see it as F sub net, the net force, right? The total amount of force acting on an object. Very important. But I like to write it with the mass acceleration first for reasons that you will see on Wednesday. But what is Newton's second law trying to tell us?
The more the force you put, the more acceleration you get.
Yes, right there. Okay? Force and acceleration, different things. What's a force? It's a push or a pull. What's an acceleration? A change in motion. Those are different things, right? But are they related to each other? Yes, the more net force you have, the greater the change in motion will be. That's what that is, right? Because they're directly proportional to each other across the equal sign. But what's a force? Good. Is it MA? No. No. Newton's second law is so misunderstood, and I don't blame you, because your math teachers probably taught you that equals means is. Equals does not mean is. Okay? If there were no M, it just said A equals F, would they be the same thing? Yes. Because that mathematical statement is just two things on the other side equal sign, right? Okay? But notice this is an M times an A. But does that make an M times an A force? Is an M times an A push or a pull? No. No. You're okay. It's normal. An M times an A is not a force. A force is a push or a pull. But if I take all the pushes and pulls that are acting on something, can I figure out what that something's acceleration is? If I know one thing, the mass. Mass is the thing that tells us how much change in motion we are going to get when we apply a force. To how many objects? There's only one mass up there. So whereas Newton's third law is about two objects interacting, Newton's second law focuses on only one. A mass will change its motion if it experiences a force. That's what Newton's second law tells us. Unfortunately, when we write it as F equals ma, what do people automatically assume? That force is mass times acceleration? No. What's force? Good. You feel like you're being brainwashed? It's a push or a pull. That's what a force is. It's not an M times an A. It just so happens that that push or pull is proportional to the change in motion through the mass. Okay, so what is mass? Size of an object, that would be the volume.
The amount of gravitational force.
Amount of gravitational force, again, you use the word force, so that's a push or a pull, and a mass is not a push or a pull.
Wait, how much is pull? How much is gravity again?
That would be weight, and weight is not mass. What's math? What's wrong? Did you guys read? I know none of you are reading the book. Oh no, you probably read, but I'm gonna blame the K through 12 system. This is the problem with America. We have people going through the K through 12 system, and you don't even know what mass is. We're doomed.
Does anything have a place in
I'm not upset because it's not your fault. It's not your teacher's fault. Okay? They did other things too that is their fault, but not this one. Because until about 12 years ago, not even physicists knew what mass was. We had a secret. We didn't know what mass was. We didn't know where it came from. We had some ideas, and it ended up being something called the Higgs boson, which was this particle that told us everything about the Higgs field, which told us why everything has mass. Did that help you understand what mass is? No, probably not. Okay? And none of that matters until physics 4C. But mass is, okay, I need an analogy. What is mass? Why are we struggling? I have no doubt that you know your mass. Like, not the number, but you experience your mass all the time. You've experienced the mass of other objects. You can tell me what object has more mass than another if I gave them to you. All of those things are true, but like when it comes to telling me what mass is, you are struggling, and I am struggling. We're all in the struggle together, and this is why. As an analogy to why it's difficult for you to explain mass to me, let's pretend, okay? And I know it's going to be a stretch of the imagination, but you're good at imagining things, so it'll be okay. Let's imagine that I am from another planet. And on my planet, we can't taste or smell anything. We just don't have the chemical receptors to do that weird human thing that you guys do, tasting stuff. Okay? I would like you in words to please explain to me what salt tastes like.
salty?
That didn't help.
Bitter? Kind of.
But bitter is something different. Bitter is what some people say broccoli tastes like. And broccoli doesn't have to be salty. Salt tastes like sweat. It still doesn't help. Explain to me in words the sensation of salt and the taste of salt. Why are you struggling?
We would need like some chemical names or something.
What?
That's like what different language doing.
Because the definition of it is gained through what? Experience. Throw a kid in the ocean, that's what salt tastes like. Right? Don't do that. You have to experience it. And once you experience it, that's what salt is. Ah, that's salty. Okay. Right? Mass at this level tastes like salt. No, it doesn't. But you know what I'm saying? We can point at it. We can tell which one's bigger or smaller. But actually saying what it is really, really difficult because it's not the amount of stuff in something, because what does that mean, stuff? Okay, right? Why does a proton have mass? What is the proton's mass? All those different things, right? Don't matter. Okay, no, I'll define. You want a definition for mass? I'll give you a definition of mass. You're not going to like it. Did that help? No. Right? Okay? But because mass, it doesn't say mass is a force divided by an acceleration. What it's trying to tell us is that mass tells us the ratio of those two things. Why is a car harder to push than a bicycle? Don't use the word inertia anymore. It has more mass, which tells you that you need to apply a lot of force to change its motion, right? Whereas a bicycle, how much force does a bicycle take to change its motion? Much less, right? Okay. Why does the couch have more mass than a chair? I have to apply more force to get it to go somewhere. Right? Mass is trying to capture this idea between force and acceleration. But let me make very clear right now. I don't know how to stress this any more strongly than I am right now. Mass is not weight. You ask somebody in America what their weight is, what are they going to do? Punch you. And when they're done punching you, they might tell you the number in pounds. Okay? Pounds is the stupid unit system's unit of force. In the metric system, force is measured in a unit called newtons. Wonder where we got that idea. Right? Okay? What's a newton? It's a really good cookie. It's filled with fig. A newton is a unit of force. Mass has a unit of kilograms. So you go to Europe and you ask them for their mass, and they'll tell you their mass in kilograms. But you usually would say, what's your weight? And the European would say, 70 kilograms. Are they giving you their weight? No, because weight would be a force which would have units of newtons. But nobody runs around saying, I'm 560 newtons. That sounds bad, doesn't it? Right? Okay. They'll say it in kilograms. Kilograms is the unit of mass, whereas pounds or newtons is the unit of force. So if kilograms and newtons are in the same unit system, right? Newtons, force, mass, kilogram. Okay? And in the English system, we have units of pounds for force. Does anybody know what the English system of units is for mass? It's the slug. Not the slimy thing that crawls along, but a slug of metal. Okay? Like a sample of metal. Okay? So yeah, it's slug. But do we wander around and go, this many slugs? Well, they do at UC Santa Cruz, but nowhere else. Okay? So, what the heck is... what's a newton? So, a newton, the unit of a newton for force, okay, what are the units of acceleration? It's a meter per second squared. What are units of mass? Kilograms. So the unit that is a kilogram times a meter per second squared is awkward to say over and over again, and so we call that a newton. Okay? Unit-wise, we have to be the same on both sides of this equation. But weight is the pull of the Earth on you. And when we get to chapter 13, it'll be other things in the solar system or the universe. But for right now, it's the pull of the Earth. And what's a pull? What's a pull? It's a force, because a push or a pull is a force, right? So weight is a force. And does your weight change if you go to the moon? Yes. Does your mass change if you go to the moon? No. Mass is independent of anything. Okay? Whereas weight, the push or pull due to gravity on you, depends on the mass of the thing that you're near and a bunch of other stuff. Okay? So weight is not mass. But if I want to find the weight, the force of gravity acting on an object, which is, I think, the symbol that your book uses, I tend to use big W for weight because it's easier to draw than F sub G. How can I find it if I know my mass? What's the situation that we've had in this class already where gravity is the only thing that's acting on you? Free fall. Can I find the weight of my keys? Sure. I need to know their mass. And what else? Their acceleration. Right? I need to know their acceleration. But I do know their acceleration. So there's weight. It's mass times gravitational acceleration. Does my weight exist as I'm standing right here on the floor right now? Sure it does. What is it? But symbolically wise. It's mg. But I'm not in free fall right now. My weight does not depend on whether I'm accelerating. I'm just saying that one way to find my weight would be to drop me, right? Okay? And know my mass and my acceleration. But my weight stays the same here because I haven't changed my mass, right? And the Earth is still trying, is the Earth still pulling on me? Yeah. Yes. But something is getting in the way. What is it? It's the floor. Right? So the floor is pushing back on me. And if I weigh 173 pounds and my motion is not changing, my acceleration is 0, what can you tell me about the net force on me?
0.
It has to be 0. Newton's second law tells you that if an object is not changing its motion, the net force is 0. I know that the net force on me is 0 because my motion isn't changing. I am being very careful. You will notice that I didn't say anything about my motion. I said my motion wasn't changing. How do you know the net force on me is 0?
The motion is not changing.
Good. There's a piece of your brain that answered because you're not moving, which is wrong. Not moving, what are we talking about if we're talking about moving? We're talking about velocity. Is velocity up there? No. What's acceleration? Change in velocity, right? Okay. Direction or magnitude. So can you give me an example where something is moving, has velocity, but has no net force?
Standing on Earth.
What?
You're standing on Earth. You're moving because it's orbiting.
Okay, well, but we're gonna assume the Earth isn't moving right now because that gets a little bit complicated.
Walking straight at a steady speed.
Walking straight at a steady speed. So if I'm over here, right, and I just walk and keep my velocity and direction the same, what is the total sum of forces acting on me? It has to be 0. How did I know the net force was 0?
Your motion, no change in motion.
I wasn't speeding up, slowing down, or turning. Right? That's what Newton's second law tells us. But the misconception in your brain, the dirty water in your bucket, is that you want to tie motion to forces. It's how the motion is changing. What is the thing on your car that guarantees 0 net force while you are moving? Cruise control. What does cruise control do? Keeps your speed the same, right? And as long as you don't turn the wheel, no matter how many forces there are, friction from the tires, the earth pushing on you, air resistance, the motor pushing forward, they are all going to add up to what? Why?
There's no change in motion.
Because you're not changing the motion. Concentrate on acceleration and don't swap acceleration for velocity. That's a huge mistake that you're going to make. You come to me, Mr. Bill, conceptual question doesn't make any sense. And I'll tell you about acceleration. You go, it'll happen. It'll be okay. It'll be all right. Okay. So, weight is not mass. Weight is a force. Mass isn't. Okay. One last thing I want to introduce you to, before I let you, we talked about that, is a tool. Now, our problem-solving method, the general idea is not going to change. Okay? We're still going to need to visualize and strategize and do a bunch of math and then go back and check to make sure that that math is consistent. But the tools we use to visualize what's going on are going to change. The tools we use to strategize are going to change. We're going to have a different toolbox. Okay? So let's get started with how we are going to start visualizing things. This is a common language that's used across engineering and physics and a little bit of mathematics, and it's called the free body diagram. It's called a free body diagram because we're going to draw a diagram of one object. So is Newton's third law going to be involved in the drawing of this diagram? No, because Newton's third law requires two objects. We're going to need to know the concept of Newton's third law, okay, to help us out, to double check to make sure our diagrams are correct. But the diagram itself is not going to indicate any Newton's third law pairs of forces. Because we're going to draw a diagram of a single object, a free body. If we're going to draw a picture of a car, we're not going to draw the road. If we're going to draw a picture of a tire, we're not going to draw the car. We're going to isolate a single object and look at the forces that are acting on it. When you go to draw a free body diagram, you have to isolate the object that you want, and then you need to draw a picture of the object. And as a demonstration, I would like you to just name an object that you would like me to draw. A pencil. Name me another object. A cat?
A triangle.
You would like a triangle? Another object. Any object. Mr. Balogh. What's the point? It doesn't matter what the object is, right? You are not drawing anatomically correct diagrams here. Okay? The free body is it's just a simple shape. You'll see me draw mostly squares. Okay? Sometimes circles. But you want to keep it really simple, whatever it is. So now let's draw a free body diagram of Mr. Balogh standing on the floor. The way you're going to do this is you need to ask yourself, what are all of the objects that are pushing or pulling on Mr. Balogh? This is where we're going to reach for Newton's third law. Because it's going to happen. You're going to invent forces that aren't there. I'm like, what do you mean, Mr. Balogh? I'm not going to invent any force. Okay. Let's do another thought experiment. Stoplight in your car. Light turns green. Gas push. Okay. Tell me the direction that the force is acting on you. Forwards or backwards? Backwards. Why did you say backwards? You got pushed into the seat, right? That is wrong. Name the object that pushed you backwards into your seat. The car? Which way did the car push on you? Forwards! Right? You changed your motion. You didn't hit the gas and go, that's what you did first. Right? Okay? You hit the gas, you were pushed forwards. Your motion changed in the forwards direction. Name the object that pushed you backwards. Nothing. Nothing pushed you backwards. Did some invisible troll jump on the hood of your car and push through the windshield and push you into the chair? Some of you are like, I've seen that. No, you were on site. Why did you invent a force to push you backwards into the chair?
That's how it feels.
Because that's what it feels like, Mr. Balogh. That's what it feels. What did you confuse for a force? Your inertia. The car was trying to get your inertia to go somewhere. And your inertia said, nah. And the car said, too bad. And it changed it, right? Changed your motion. You assumed correctly that you were the center of the universe. Remember, you have that power. Okay? It's just that your frame of reference is now an accelerated frame of reference, which gives rise to fictitious forces. So how do we combat fictitious forces? Newton's third law. Newton's third law, the song. How many objects must there be for a force to exist? 2. If you draw a force on a diagram and you cannot name the object that created it, there's a good chance you're inventing something. So for Mr. Balogh standing on the ground, what objects, one or more, are pushing or pulling on me? The ground, the floor here, right? And which way is it pushing on me? Probably upwards. Okay? All forces need a label. Notice that is a vector. Why is it a vector? Forces have magnitude and direction. I'm going to call that one the normal force. The normal force is the name for all forces that we give when two objects come in contact with one another. The force is perpendicular to the surface, and in mathematics, another way to say perpendicular is normal. So the normal is all about direction, perpendicular to the surface of contact. Okay, so the floor is pushing up on me. Call it the normal force. Is there any other object? No, okay, so I'm pushing on other things, but that's not what the free body diagram is about. This is about Mr. Balogh. So what are the objects that are pushing or pulling on me? The floor is pushing up. Gravity is not an object. The earth, via the force of gravity, is pulling down. Otherwise known as my weight, which I usually draw as mg. Now, how do I know that this is a correct free body diagram for Mr. Balogh standing on the floor? If you look at those two vectors and you add them together, what are you going to get? 0. How do I know the net force is 0? Good. My motion isn't changing. Those of you that wanted to say because you're not moving, that's the incorrect thing we want to strike from your brain. We want to concentrate on whether the motion is changing. Right? I don't know why that disappeared, but it did. Maybe because it knows class is over. Right? When we come back on Wednesday, we are going to take these ideas. Do all the concept for chapter 5 homework. You can do that. Okay? We're going to get into the mathematics of Newton's second law, and it's going to get bad really fast. You're going to be shocked at how bad this can get from a really simple... Newton's second law, F equals ma. It can't be that bad, right? It's going to be bad. See you Wednesday.